The first lesson in thermochemistry is on heat and temperature. This lesson will really serve as the basic for everything we will do in this unit. Lots of terminology and some vocabulary that we'll be using along with some basic energy conversions. Here are the learning targets for this lesson. You can see there are 5 of them here. First thing we want to be able to do is to differentiate between the terms heat and temperature. Heat, or otherwise known as heat energy or thermal energy, it is related to the motion of particles of a substance. Anytime you see any of these terms, heat energy, or thermal energy, they all refer to the same thing. We will use them interchangeably. So the more heat a substance has, the greater the motion of its particles, meaning the particles will travel faster and they'll also cover more distance in their travel. The total amount of heat in an object is simply the sum of the individual energies that all of the particles in that object have. So we just add them all up, and that would be the amount of thermal energy in that substance. Temperature, on the other hand, is the average kinetic energy of all the particles of a substance. So we would take the average, or we would take the energies of all the particles, we add them all up, and then we divide by the number of particles, and that would give us the temperature, in other words, the average kinetic energy of those particles. Temperature and heat are related, but they are not the same thing. If we increase the temperature of a substance, that would also increase the amount of thermal energy or heat that substance has. However, heat, unlike temperature, it also depends on how much substance is present. Here's an example. Suppose we had a bathtub of warm water. That bathtub would have more thermal energy or heat than a cup of scalding hot coffee because there is more water in the tub. So even though the temperature of the coffee is obviously greater than the water in the bathtub, because there's simply way more water in the tub than there is in the coffee, it would have more heat energy or thermal energy than the coffee would. Here are a couple of video clips that demonstrate the difference between heat and temperature. I think they're both pretty good. I can't click on them here in the video. I have linked them, however, on the website. I would encourage you to check them out at some point. I think they are both very good at demonstrating this difference. I also have a picture here to help us demonstrate the difference. What we see here are 2 beakers of water. One contains 2 liters of water, the other contains 1. And the picture is supposed to show that they're both boiling. And so they're at the same temperature. I know you can't really see the thermometers here, and I don't even think these thermometers are labeled right. But they're both supposed to be 100 degrees Celsius. So both of these beakers of water are at 100 degrees Celsius. The water is boiling. However, the beaker that contains 2 liters of water would actually contain twice as much heat energy or thermal energy than the beaker that contains 1 liter of water, because there's twice as much water over here. Because they're both boiling, we know they're at the same temperature, but there'd be more energy, heat energy here with the larger beaker. We want to be able to apply the terms system and surroundings to different situations. When we refer to the system, what we are referring to is the object or collection of objects that are being studied. The surroundings, that would be everything outside of the system that can exchange energy with the system. And if we ever see the term universe, that simply refers to both the system and the surroundings together. So here are some examples. First of all, on the picture on the left, we have a flask that contains something going on in there. It could just be water. Maybe it's a reaction that's going on. And we are saying that that is what we are studying, is the reaction inside the flask. So whatever that is in blue there, that is our system. That is what we are studying. Everything outside the system that can exchange energy with that system, so this would be the immediate volume of air surrounding the flask and the flask itself. Notice the flask is also shaded in blue. That would be the surroundings. And then if we include all of that, what's inside the flask and the volume around the flask, that would be the universe. Here's another example. In this case, we have a cube, an ice cube, floating in some water. And this picture is saying that the ice cube and the water are the system. And then the surroundings would be everything else. The cup that it's in, the immediate air around the cup, that would be the surroundings. Now, one thing to note, we wouldn't have to include the liquid water and the ice in the system. Perhaps we just wanted to say that the ice cube itself was the system, and then the liquid water would be considered part of the surroundings. Likewise, we could say that the liquid water is the system, and the ice cube and the cup and the air would be the surroundings. There is no definite boundary of any system. It is simply defined by the experimenter. And here's a good example of that. Here we have a candle that's burning, and obviously there is no actual boundary that separates the system from the surroundings. In this case, the system boundary, or what we consider the system, would just be this imaginary dotted line going around it. Everything inside of that would be considered the system, and everything outside of that would be considered the surroundings. But there's no real boundary there. It is simply our own creation as the experimenter as to what the system and the surroundings would be. We want to be able to explain the direction of heat transfer and the concept of thermal equilibrium. Thermal energy, or heat, it always flows from objects with a higher temperature to objects with a cooler temperature. Here's a picture to help us demonstrate that. In this picture, we have two different metal blocks, and who knows what they are. Let's say they're metal, one being labeled A, one is B. Block A has a higher temperature, thus it is shaded in red. Block B is at a cooler temperature, thus it is shaded in blue. Now let's say we put these two blocks together. Heat energy will travel from block A to block B, and that's being represented by the red arrow here. Because A is at a higher temperature, B is at a bluer temperature. B is at a cooler temperature. Let's try that again. Notice now the shading is starting to become more similar, because as heat is being transferred from A to B, the temperature begins to change. Block A begins to cool down, block B begins to warm up. Now this is going to continue until both of the blocks are in thermal equilibrium. In other words, they're at the same temperature. That's what thermal equilibrium means. Once that is reached, notice the color of both blocks is now the same. They are now more of a purple shade, a combination of red and blue. The heat flow has stopped because they are in thermal equilibrium. Here are a couple other pictures that help us to demonstrate this heat transfer. If we have two objects, again, one warmer, one cooler, we can see the thermometer here, the warmer object higher on the thermometer than the cooler object. Heat is going to be transferred from warmer to cooler to that cooler object. Notice they don't actually have to be in contact. This would be like if you took your hand and stuck it next to a really hot metal bar. You don't have to actually touch the bar to feel that it's hot. You can feel the heat being transferred to your hand simply by sticking it close to the bar. And if you leave it there for long enough, you will eventually, your hand will be the same temperature as the bar, is that bar is going to cool until it gets to room temperature, just like your hand would. Here is a picture that relates the terms system and surroundings that we learned on the previous learning target. On the left here, we have a system that is hotter than the surroundings. So notice the arrows going away or out of the system represent heat energy leaving the system and going to the surroundings. This will occur until the system is at the same temperature of the surroundings. So what will happen then is the temperature of the system goes down, the surrounding temperature would increase until they're at the same temperature. On the right here, we have a system that is cooler than the surroundings, so heat energy is flowing into the system, and this will occur until the system is at the same temperature as the surroundings. So here the temperature of the system increases while the surroundings temperature would decrease, and again that would occur until they reach thermal equilibrium. Next learning target, we want to use the terms endothermic and exothermic. An exothermic process is a process where heat is transferred from the system to the surroundings. So here we have our system, which is demonstrated with this red box, and energy is leaving the system and going to the surroundings. In other words, we say that energy is released. An example of the release of energy or an exothermic process would be the freezing of ice to form, freezing of water, liquid water, to form ice. So we can see that energy is leaving the liquid water. That's what this arrow is showing, and that process will result in that liquid water freezing to form solid ice. An endothermic process is just the opposite. Heat is transferred from the surroundings to the system. So just flipping the arrow around from the previous picture, here we have our system in the red box. Energy is being added to the system from the surroundings, or we might say that energy is absorbed by the system. So the opposite process to that we looked at before would be the melting of ice. If we have an ice cube and it is absorbing energy from the surroundings, it will melt to form liquid water. That would be considered endothermic. Our last learning target, we want to relate and convert between energy units. The SI unit of energy is the joule, and it is symbolized by the capital letter J. The thing about the joule is it is a very small amount of energy. So it really isn't convenient to use that as a unit. If we're going to use the joule, we'll actually more practically use the kilojoule, which is 1,000 joules. We know that because kilo means 1,000. The symbol for the kilojoule would simply be the lowercase letter k with the capital J. So that is much more practical for us to use in chemistry. An older unit of energy that you are more familiar with is called the calorie. The symbol for the calorie is simply the lowercase letter CAL. 1 calorie is equal to 4.184 joules. Now you will want to memorize this conversion factor. I might make a note of that. 1 calorie equals 4.184 joules. You'll want to memorize that one. However, this particular unit, calorie, is not the one you are most familiar with. The one you are most familiar with is the dietary or the nutritional calorie. Note it is spelled with a capital letter C. That's how we differentiate between the nutritional calorie and I suppose what we might just call the regular calorie. And the nutritional calorie is simply 1,000 calories or a kilocalorie, or sometimes called a kcal. And note the symbol for that, if we want to write that, is the lowercase letter k followed by CAL, just like we do for calorie. Now we should be able to convert between any of these units of energy. So here are a few examples of that. First question, how many joules are in 187.5 calories? Notice that this is the lowercase letter c in calories, so this is just a normal calorie. To do this, we just want to use the conversion of 4.184 joules equals 1 calorie. Notice we want calories on bottom so that it cancels with the unit that we're starting with. So calories would cancel, we would be left with joules. And then we would have 4 sig figs because the 187.5 is 4, as is the 4.184. That is not an exact conversion. That is limited to 4 sig figs if that issue ever comes up. And in this case, it would round to 784.5 joules. Next question. Determine the number of calories in 2,952 joules. Notice this calorie is spelled with a capital C, so this would be the nutritional calorie, or a kilocalorie. So for this one, we'd want to start with the information given to us, the 2,952 joules. And then we want to convert that to calories. Notice just the normal calories with the lowercase c. Joules would cancel, and we divide by 4.184 because there's 4.184 joules in a calorie. Now to go to the nutritional calories, we want to use the conversion factor of 1,000 calories in a nutritional calorie. Notice the difference here, the lowercase c and the capital C. The calories with the lowercase c would cancel. And then that would leave us with 0.7055 nutritional calories, which again is indicated with the capital letter C. That is all the content for this lesson. There are a few more slides here, so you do want to keep watching. These next slides contain some review and practice questions. What I would encourage you to do is to read the question, pause the video, develop your own answer or solve the problem depending on what you're asked to do, and then continue with the video to see my answer. On these questions that are conceptual, certainly your answer might be different than mine, so focus on the content of what is being said, not exactly how it's being said or the examples. This will help you to understand whether or not your answer is correct. First question, we want to compare and contrast the terms heat and temperature. Both heat and temperature, they are related to the motion of particles in a substance, so that's how they're similar. As the temperature of a substance increases, its particles move faster, and thus the amount of thermal energy would also increase. So they are similar in that manner. However, temperature is an intensive property. This means that it does not depend on how much substance is present. So an example of that would be, say we had a cup of coffee and it were at 80 degrees Celsius. If we take that cup of coffee and we pour half of the coffee down the drain, the remaining coffee still has a temperature of 80 degrees Celsius. It doesn't matter that there's less of it. The temperature hasn't changed because of that. However, heat energy, that is extensive, meaning that it does depend on how much substance is present. Back to the coffee example, if I pour out half the coffee down the drain, my coffee cup now contains half the amount of heat energy than it did before, because there's half the amount of coffee. Another example, and this is what I have written here, is say we have a cup of hot water. It has a greater temperature than a swimming pool full of ice water, obviously because it has a greater temperature. However, the pool of ice, it has more heat energy because if we add up all the energies of all the water molecules that make up that pool, it would be more than the sum of the energies that make up the molecules of water in the cup of hot water. Simply because there's way more water in that swimming pool than there would be in that small cup. Question 2. You place a cup of hot coffee on a kitchen counter for several minutes. What happens to the temperature of the coffee? To the surroundings? Explain. The temperature of the coffee is going to decrease while the temperature of the surroundings would increase. This is going to occur because heat will always flow from the object with the greater temperature, in this case the coffee, to the object with the cooler temperature, in this case the surroundings. That could be the air around it, the coffee cup itself, maybe your hand that's holding the coffee cup. So the heat is always leaving the coffee and it's entering the surroundings, so that's why the temperatures change as they do. Explain why placing the cup of hot coffee on the counter will not result in the coffee beginning to boil. If the coffee were to boil, that means it would require energy from the surroundings to do this. So energy would have to flow from the surroundings into the coffee in order to get that coffee to boil. Well, this would result in heat energy flowing from the cooler substance, the surroundings, to the warmer substance, the coffee. In this direction of heat flow, it never occurs. So, thus the coffee will not boil. Question 4. What term is used to describe the object or objects being studied? That would be the system. Question 5. What are surroundings? Surroundings are any area outside of the system that can exchange energy with the system. Question 6. Classify each process as endothermic or exothermic. First one, boiling water. So let's say the water is our system. Let's ask ourselves, is energy being added to the system or is it being removed from the system? Well, if we're going to boil water, the water has to have energy added to it in order to get it to boil. That's why you put your pot of water on the stove and you turn it on and you let it absorb energy. So in this case, the system is absorbing energy from the surroundings. That makes it endothermic. Next question. Let's say we are lighting a candle. Now let's consider the wick of the candle to be our system. Ask ourselves, are we adding energy to the system or removing it from the system? Well, to light the candle, we have to add energy to that wick, don't we? So in this case, the system is absorbing energy, and again, that is endothermic. Next question. Let's consider the same candle, but now it's burning, so we've already lit it. And again, let's say our system is the wick. Well, that wick is releasing light, which is energy. It's releasing sound, perhaps if you listen really carefully. It's also releasing heat energy, and we know that because if we stick our hands up next close to it, we can feel that energy being released. So that energy is leaving the system. That makes it exothermic. Question 7. How many kilojoules are in a can of soda containing 230 calories? Notice this calories is the capital letter C, so this is the nutritional calories. We'd want to start our problem with that 230 nutritional calories and convert it to kilojoules. So our conversion would probably look something like this. We would first convert our nutritional calories, again that's the capital C, convert that into calories. There are 1,000 calories in a nutritional calorie, so the capital letter C calories would cancel. We can then convert to joules using the conversion of 4.184 joules per calorie, and again notice the calories would cancel. And then finally, to convert to kilojoules, we could say that there are 1,000 joules in a kilojoule because kilo means 1,000. And again, joules, those would cancel, and we're left with kilojoules. As far as sig figs are concerned here, notice 230 as that's written, that's just 2 sig figs. So we can only have 2 sig figs in our answer, which would round to 960 kilojoules. Question 8. A 900 kilogram SUV traveling at 30 meters per second has a kinetic energy of 405,000 joules. We were asked to determine the number of calories that this energy is. So this first information, the 900 kilogram SUV and the 30 meters per second, that's really not of any importance to us. It's just informational to let us know how we would get this 405,000. But anyway, we want to end with calories. Notice the capital letter C, so nutritional calories. We're going to start with our 405,000 joules. So we would convert from joules to calories using the 4.184 joules in 1 calorie. Notice joules would cancel. And then we could convert to nutritional calories using 1,000 calories in a nutritional calorie. The calories would cancel. And one thing I think that's interesting about this is the small number of nutritional calories this is. Notice this is a little less than 100 calories, as we would simply say it if we were talking about our diet, which would be a very small snack. 100 calories is not very much. Comparing that to an SUV traveling down the interstate at 30 meters per second, which that would be about, 72 miles per hour, somewhere in there, which obviously we wouldn't want to get hit by that SUV. That would be a huge amount of energy. Relating that to how much energy we consume, it's very, very small. We can see again this is a very small snack worth of calories. So the amount of energy our body uses in a day is absolutely astounding, I think, when you compare it to energies associated with motion, which would be talking about here with this SUV going down the road.